Welcome to Copernicus AI, Frontiers of Science. I'm Matilda, and today we're diving into the fascinating world of optimization theory and gradient-free methods. Adam, what makes the recent research in this area so revolutionary?
Thanks, Matilda. It's a pleasure to be here. The shift we're seeing is quite significant. Traditionally, optimization relied heavily on gradient-based methods. These methods use the gradient, or the slope, of a function to find its minimum or maximum. However, calculating gradients can be computationally expensive or even impossible in many real-world scenarios. The revolutionary aspect is the increasing development and application of gradient-free methods, which don't require gradient information. For instance, Abdinur Bulasnain's work on evolutionary dynamic optimization and machine learning, available on arXiv, explores how evolutionary computation, inspired by natural selection, can provide robust optimization solutions without relying on gradients.
That's fascinating. So, instead of calculating slopes, these methods mimic natural processes? Can you give us a more concrete example?
Absolutely. Evolutionary algorithms, like genetic algorithms, maintain a population of potential solutions and iteratively improve them through processes like selection, crossover, and mutation. Think of it like breeding the best traits in a population over generations. This is particularly useful in dynamic optimization problems, where the objective function changes over time. Bulasnain's work highlights the adaptability of these methods, showcasing their ability to handle complex, non-differentiable, and even time-varying optimization landscapes. This is a major departure from traditional methods that often struggle in such environments.
It sounds like a completely different approach. What are some of the challenges that gradient-free methods face?
Good question. While gradient-free methods offer significant advantages, they also have their limitations. One major challenge is computational cost. They often require evaluating the objective function many times to find a good solution, which can be time-consuming, especially for complex problems. Another challenge is the lack of theoretical guarantees. Gradient-based methods often come with convergence proofs, ensuring that they will eventually find the optimal solution under certain conditions. Gradient-free methods, on the other hand, can be more difficult to analyze theoretically, and their convergence behavior may be less predictable. However, ongoing research is addressing these challenges, as we see with Tengyu Xu and colleagues' paper on gradient-free minimax optimization, variance reduction, and faster convergence, which explores techniques to improve the efficiency and convergence of gradient-free methods in minimax problems.
Minimax problems. That sounds like a specific area. What are some other specific applications where gradient-free methods are proving particularly useful?
They're proving invaluable across several domains. One prominent area is hyperparameter optimization in machine learning, as Li Yang and Abdallah Shami discuss in their paper on hyperparameter optimization of machine learning algorithms, theory and practice. Finding the best hyperparameter configuration for a machine learning model is crucial for its performance. Gradient-free methods are particularly well-suited for this task because the relationship between hyperparameters and model performance is often complex and non-differentiable. Another area is structural design. Mehran Ebrahimi and colleagues in their work on optimal design of frame structures with mixed categorical and continuous design variables using the Gumbel softmax method demonstrate how gradient-free methods can be used to optimize the design of frame structures with discrete and continuous design variables, which is a common challenge in engineering.
So, from machine learning to structural engineering, it seems like these methods are quite versatile. How does this impact the field of artificial intelligence?
It's a game changer. By enabling optimization in scenarios where gradients are unavailable or computationally prohibitive, gradient-free methods broaden the scope of AI applications. They allow us to tackle more complex and realistic problems, leading to more robust and adaptable AI systems. For example, consider reinforcement learning, where an agent learns to make decisions in an environment by trial and error. Gradient-free methods can be used to optimize the agent's policy without relying on a differentiable model of the environment. This is particularly useful in scenarios where the environment is complex or unknown. Furthermore, the research by Hassan Rafiki et al. On weakly convex-concave min-max optimization, provable algorithms and applications in machine learning suggests improvements in handling non-convex problems, thus expanding the applicability of these methods.
That's a compelling point. What about the connection to more traditional optimization methods? Are they becoming obsolete?
Not at all. Gradient-based methods still have their place, especially when gradients are readily available and the problem is well-behaved. In fact, there's a growing trend of combining gradient-based and gradient-free methods to leverage the strengths of both approaches. For example, one might use a gradient-free method to get a rough estimate of the optimal solution and then refine it using a gradient-based method. Also, as Sebastian Bubeck outlines in Convex Optimization, Algorithms and Complexity, convex optimization still forms the bedrock of many optimization problems, providing theoretical guarantees and efficient algorithms.
That makes sense. It's more about expanding the toolbox rather than replacing existing tools. Where do you see this field heading in the next few years?
I expect to see continued advancements in the efficiency and scalability of gradient-free methods. Researchers are actively exploring techniques like variance reduction, parallelization, and surrogate modeling to reduce the computational cost of these methods. We will also see more sophisticated theoretical analysis, providing better guarantees on their convergence behavior. Furthermore, I believe there will be increasing integration of gradient-free methods with other AI techniques, such as deep learning and reinforcement learning, leading to new and innovative applications. The work by Haipeng Luo et al. On accelerated parallel optimization methods for large-scale machine learning is a step in this direction, highlighting the importance of scalable algorithms.
It sounds like a very promising future. Before we wrap up, can you touch on how these optimization techniques are being applied outside of machine learning and engineering?
Certainly. Optimization techniques, including gradient-free methods, are used in a wide array of fields. In finance, they can be used to optimize investment portfolios. In logistics, they can be used to optimize delivery routes. And even in healthcare, as shown in the work by Richard C. Barnard and Christian Clayson on L1 penalization of volumetric dose objectives in optimal control of PDEs, optimization can be used to optimize radiation therapy plans for cancer treatment. The key is identifying the objective function and the constraints, and then choosing the appropriate optimization method to find the best solution. There are even applications in areas like non-negative matrix factorization, as explored by Valentin Leplot, Yuri Nesterov, Nicholas Gillis, et al. In their paper, Conic Optimization-Based Algorithms for Non-Negative Matrix Factorization, showing the breadth of optimization's reach.
Adam, this has been incredibly insightful. It's clear that gradient-free optimization methods are not just a niche area, but a powerful force reshaping how we approach complex problems across diverse fields. Thank you for shedding light on this groundbreaking research and its potential impact.
My pleasure, Matilda. It's an exciting field with a lot of potential, and I'm glad I could share some insights.